Logarithmic properties. In the previous section, we derived two important properties of logarithms, which allowed us to solve some basic exponential and logarithmic equations. Properties of logs. Inverse properties. Log base b of b to the x power equals x. B raised to the log base b of x equals x. Exponential property. Log base b of a raised to the r power equals r multiplied by log base b of a. Change of base. Log base b of a equals log base c of a divided by log base c of b. While these properties allow us to solve a large number of problems, they are not sufficient to solve all problems involving exponential and logarithmic equations. Properties of logs. Sum of logs property. Log base b of a plus log base b of c equals log base b of a multiplied by c. Difference of logs property. Log base b of a minus log base b of c equals log base b of a divided by c. It's just as important to know what properties logarithms do not satisfy as to memorize the valid properties listed above. In particular, the logarithm is not a linear function, which means that it does not distribute. Log of a plus b does not equal log of a plus log of b. To help in this process, we offer a proof to help solidify our new rules and show how they follow from properties you've already seen. Let a equal log base b of a and c equal log base b of c. By definition of the logarithm, b raised to the a power equals a and b raised to the c power equals c. Using these expressions, a multiplied by c equals b raised to the a power multiplied by b raised to the c power. Using exponent rules on the right, a multiplied by c equals b raised to the a plus c power. Taking the log of both sides and utilizing the inverse property of logs, log base b of a multiplied by c equals log base b of b raised to the a plus c power equals a plus c. Replacing a and c with their definition establishes the result. Log base b of ac equals log base b of a plus log base b of c. The proof for the difference property is very similar. With these properties, we can rewrite expressions involving multiple logs as a single log, or break an expression involving a single log into expressions involving multiple logs. Example 1. Write log base 3 of 5 plus log base 3 of 8 minus log base 3 of 2 as a single logarithm. Using the sum of logs property on the first two terms, log base 3 of 5 plus log base 3 of 8 equals log base 3 of 5 multiplied by 8 equals log base 3 of 40. This reduces our original expression to log base 3 of 40 minus log base 3 of 2. Then using the difference of logs property, log base 3 of 40 minus log base 3 of 2 equals log base 3 of 40 divided by 2 equals log base 3 of 20. Example 2. Evaluate 2 log of 5 plus log of 4 without a calculator by first rewriting as a single logarithm. On the first term, we can use the exponent property of logs to write 2 log of 5 equals log of 5 squared equals log of 25. With the expression reduced to a sum of 2 logs, log of 25 plus log of 4, we can utilize the sum of logs property. Log of 25 plus log of 4 equals log of 4 multiplied by 25 equals log of 100. Since 100 is equal to 10 squared, we can evaluate this log without a calculator. Log of 100 equals log of 10 squared equals 2. Try it now. Without a calculator, evaluate by first rewriting as a single logarithm. Log base 2 of 8 plus log base 2 of 4. Example 3. Rewrite natural log of x to the 4th power multiplied by y divided by 7 as a sum or difference of logs. First, noticing we have a quotient of two expressions, we can utilize the difference property of logs to write natural log of x to the fourth power multiplied by y divided by 7 equals natural log of x to the fourth power multiplied by y minus natural log of 7. Then seeing the product in the first term, we use the sum property, natural log of x to the fourth power multiplied by y minus natural log of 7 equals natural log of x to the fourth power plus natural log of y minus natural log of 7. Finally, we could use the exponent property on the first term. Natural log of x to the fourth power plus natural log of y minus natural log of 7 equals 4 natural log of x plus natural log of y minus natural log of 7. Interestingly, solving exponential equations was not the reason logarithms were originally developed. Historically, up until the advent of calculators and computers, the power of logarithms was that these log properties reduce multiplication, division, roots, or powers to be evaluated using addition, subtraction, division, and multiplication, respectively, which are much easier to compute without a calculator. Large books were published listing the logarithms of numbers, such as in the table to the right. To find the product of two numbers, the sum of log property was used. Suppose, for example, we didn't know the value of 2 times 3. Using the sum property of logs, log of 2 multiplied by 3 equals log of 2 plus log of 3. Using the log table, log of 2 multiplied by 3 equals log of 2 plus log of 3 equals 0.3010300 plus 0.4771213 equals 0.77811513. We could then use the table again in reverse, looking for 0.77811513 as an output of the logarithm. From that, we can determine log of 2 multiplied by 3 equals 0.77811513 equals log of 6. By using addition in the table of logs, we were able to determine 2 multiplied by 3 equals 6. Likewise, to compute a cube root, like the cube root of 8, log of the cube root of 8 equals log of 8 raised to the 1/3 power equals 1/3 log of 8 equals 1/3 multiplied by 0.9030900 equals 0.3010300 equals log of 2. So the cube root of 8 equals 2. Although these calculations are simple and insignificant, they illustrate the same idea that was used for hundreds of years as an efficient way to calculate the product, quotient, roots, and powers of large and complicated numbers, either using tables of logarithms or mechanical tools called slide rules. These properties still have other practical applications for interpreting changes in exponential and logarithmic relations. Example 4. Recall that in chemistry, pH equals negative log of H+. If the concentration of hydrogen ions in a liquid is doubled, what is the effect on pH? Suppose C is the original concentration of hydrogen ions and P is the original pH of the liquid, so P equals negative log of C. If the concentration is doubled, the new concentration is 2C, then the pH of the new liquid is pH equals negative log of 2C. Using the sum property of logs, pH equals negative log of 2C equals negative multiplied by log of 2 plus log of C equals negative log of 2 minus log of C. P equals negative log of C, the new pH is pH equals P minus log of 2 equals P minus 0.301. When the concentration of hydrogen ions is doubled, the pH decreases by 0.301. Log properties in solving equations. The logarithm properties often arise when solving problems involving logarithms. First, we'll look at a simpler log equation. Example 5. Solve log of 2x minus 6 equals 3. To solve for x, we need to get it out from the inside the log function. There are two ways we can approach this. Method 1. Rewrite as an exponential. Recall that since the common log is base 10, log of a equals b can be written as the exponential 10 raised to the b power equals a. Likewise, log of 2x minus 6 equals 3 can be rewritten in exponential form as 10 raised to the third power equals 2x minus 6. Method 2, exponentiate both sides. If a equals b, then 10 raised to the a power equals 10 raised to the b power. Using this idea, since log of 2x minus 6 equals 3, then 10 raised to the log of 2x minus 6 power equals 10 cubed. Use the inverse property of logs to rewrite the left side and get 2x minus 6 equals 10 cubed. Using either method, we now need to solve 2x minus 6 equals 10 cubed. Evaluate 10 cubed to get 2x minus 6 equals 1,000, 2x equals 1,006, x equals 503. Occasionally, the solving process will result in extraneous solutions, answers that are outside the domain of the original equation. In this case, our answer looks fine.